We would like the overhead projector. The overhead slide projector here.
There's a separate table set up that we can use right here. We don't want. You were controlling from up there, but there is some way to set up down here. Do you know how to do that?
It's like for slides.
It's used for slides, but we can use for other things.
Hello, hello.
Hello. Good. Should we start? It's past magic time.
Okay.
All right.
I think it's
It is magic time.
it's even beyond magic time.
I did magic time without you.
It's the magical time.
Magical time. Okay.
Ready?
Ready?
Welcome, EECS16A. Woo!
Oh, Mickey is back, by the way. Okay, before I start on to serious business, unfortunately, we caught some cheaters in this class. So they are going to have serious consequences. The consequence is that you failed the class and that we report you to the student conduct office. So that goes in your record. So, of course, the cheating happened in homework, which makes no sense since homework in this class is here to help you learn the material. Everyone could get 100% in homework because you can see the solutions and resubmit the homework. So cheating on homework is the worst type of cheating because you're cheating for nothing, just because you want to cheat. That upsets me because that's coming from the inside, right? So if you know of people that are cheating, feel free to tell us. We will give them consequences because there's nothing worse than someone doing hard work and others getting away with cheating. So we caught many. We don't want that to happen again. Yeah, especially a midterm is coming. So what's the point?
What they're thinking?
I don't get it.
Here, I'll just be also serious.
You can't get too close, otherwise we go like, wee. Yeah.
Feedback.
Like,
positive feedback.
Wee.
So.
Anyway.
Yeah, I mean, we told you at the beginning, you know, there's going to be a time where you're going to feel, you know, that maybe this is the best way for you to succeed and stuff. And then you shouldn't, because you should see our faces. Well, we're going to have a few people in our offices
crying,
looking at those faces, crying. Oh, I didn't mean to. Oh, I'm so sorry. Let me explain to you. It's like, and we don't care. At that point, we already don't care. So we'll care if you come to us. Oh, we're having trouble. You know, not doing it so well in the class. What can I do in order to help the class? But once you've cheated, you know, you lost at least my attention. You lost our attention.
Yeah.
So that's one thing. So just be aware.
Anyway, they are probably not attending class. But I wanted to tell you here in class because sometimes you see that people are, some people watch the video. But if you see that this is happening, don't feel bad and don't feel that it's going unnoticed. It's not fair for anyone. And this notion that, oh, I can cheat my way out of Berkeley, wrong. Okay. But today, we prepared a really cool class for you guys. While they are setting up, I'm going to be talking about what we are going to ask you during the midterm. So it pays off to come to class. Let's start with question 1.
Yep. Question 1.
Okay. No. You should be very aware of what's going to be in the midterm. All module 1. You can take pictures if you want, but this was sent to you many times. And I hope that today I can speak better. Okay, well, let me move the microphone up so I don't need to say things so loud. Okay, so this is the list of topics, and midterms happening on Monday. Be prepared for it. Your homework, discussions, and everything that you have done so far will help you prepare for the midterm. Even the lab helps you prepare for the midterm. Okay. Then let's... okay, I'll go back to... last lecture. What did we do last lecture? Last lecture we went through all the steps that you should follow in order to do circuit analysis. You will see that some of these steps will become automatic for you as you progress in this class. That's the goal here. So we look at all 8 steps of circuit analysis with a very simple circuit, and then with our first block that we are going to be using in our designs here. which was the so-called voltage divider. We also looked at the rules that we apply when we are doing the circuit analysis. So we apply KCL, KVL, element definition, voltage definitions, and those rules allow us to build the equations that we need in order to analyze the circuit. Then I showed you that you could solve that system of equations with what you learned in Module 1. You could solve that by formulating your matrix and having your knowns and measurements, and then you get to a solution. But I also showed you that we could also do substitution and come to a solution for that. So we stopped here. There was a mess. The next class had midterm. Everybody was making a noise. But so I didn't finish the big message of last class, which is, okay, we had the circuit, the voltage divider, which looked something like this, where we had a voltage source, and we had two resistors connected this way. Then we called R1 and R2. We called this one Vs for our voltage source. We called this node our reference node, where potential was 0 by definition because we chose that to be the case. Then we had this one as U1, potential 1, and we have here U2. And then these 5 equations that we had here were relating current going through the 3 elements that we had here. So current 1, current 3, and current 2. We applied the element definition for the resistors, Ohm's law, to have this relation here between resistance and current. And what we wanted to solve was to solve this system of equations for currents and potentials, right? Okay, so all it was missing for us to conclude here was to find out what U2 is. So go ahead, tell me, what's U2? You have the equations, you have everything that we did last class. We concluded that all the currents that we labeled were the same. We got a negative sign here for current 3 because we established the direction of current 3 in the opposite than it should be. So it showed in our results as a negative sign. Now we need to find out what's U2 quickly. Should be easy for you. Substitute in some equation. Don't look at me. Look at your notes. Calculate. Yeah? Practice, practice. You have all the equations. We have what I1 is, what I2 is, what I3 is. You have all the equations that relate U1 and U2. You can choose, for example, equation 4. That would be very easy to find out what U2 is. I'll wait. Did it work, Mickey? Okay. You can test while they're testing their algebra. HDMI 2. Ta-da. Okay. Great. Anybody wants to offer the answer? What's U2? Looks like
if you plug it into equation 4, you get R2 Vs divided by R1 plus R2.
That's correct. If you use equation 4, you will get R2, oops, wrong 2. You will get R2 times Vs over R1 plus R2. Anybody else got this result? Yeah, it's pretty nice. This is a very nice result. Why? Actually, let me take my Scribble Scrabble here, and let's just look at this. this part here. This part is a ratio between resistors, right? Resistors in our circuits are known quantities because we go to a shell and we pick the resistor that we want to use, so we know that. And what we are saying here is we have a voltage source that we are going to apply to give power to our circuit. And now we can play with the resistor's values to change the potential right here in the middle of these resistors. So let's say, assume that you have resistors just of a value of R, okay? So if your resistors are the same value, what's going to happen to the potential there between those two resistors? Will be R over 2Rs. It's going to be half, right? So you are dividing the potential that you put into the resistor, into the circuit. Sometimes you may want to divide in half, sometimes you may want to divide in other fractions, but it's basically a tool that you have where you can decide what's going to be a potential of a node, okay? Which then, of course, you can go there and measure that node. And shall we do that?
Ooh.
Yeah? Are you ready? So we have some voltage dividers here that we prepared for you. And we are going to measure the potential.
We are.
So first, only voltage divider, okay? Don't get carried away.
Let's measure, first of all,
First,
we'll measure the value of the resistor.
the values of the resistor that are given in
What unit?
unit. Always know your units. Check your units.
She brought my glasses.
Oh, do you need mine? It's good that we are getting old together.
Jeez.
Do you need help? How shaking hands, can't see. It's downhill.
It's white on white.
Oh, come on.
There you go.
Oh, Yofi. Okay.
That's a 48.3 ohms. It's supposed to be 47, but because there's always inaccuracy of about, this particular ones are plus minus 5%. So they're not guaranteed to be exactly.
Makes sense.
The other one that's connected in series to it is also the same one. Okay, so I'm not going to go through this, but if we
Similar
measure
values.
similar values,
Similar or the same?
the same.
Okay.
And then across both of them, now you see that there's 95.5, which is basically twice the value that we had before.
Remember those values.
Okay. Now we're going to measure the other set of voltage dividers, just so we know. Okay.
Okay, just
tiny.
hold steady there.
It's just so tiny.
You hold steady, I bring the connection to
Thank
you.
you.
Okay. There.
All right. So this is one. It's not 1 ohm. It's actually 1 mega ohm. Okay, so it's 1 million ohms compared to the 47 ohms that the other one had.
How does he know? Because we selected here 2
we selected,
mega.
we
That's
selected
the
here
range.
Okay, so 2 mega. Everybody should have one of these at home. So nice.
Do
Okay.
you? Who has it? Oh, they're really cheap.
Yeah, it's like $7. And then across the entire thing is really two, I guess.
Oh, there's no connection.
Oh, it's 2
There
mega.
you go.
Yeah,
2
it's 2
mega ohms.
Okay. So
Okay.
2 mega ohms is pretty cool. All right. So yeah, that's great. And now where's this supposed to show?
Okay, so we have R1 and R2 for 2 separate circuits, okay? What's missing to be our true voltage divider here? The voltage, the power source. Could be a battery. We brought a sophisticated voltage source that gives you more range, and you can actually choose the output. While in a battery, it's a given output. Okay.
Okay, we'll put it around 3 volts.
Yeah. Mm-hmm.
Okay. And then what we're going to do now is we're going to connect one side of the circuit to this, and we're going to start with the 1 mega ohm, right? Once. So this is 1. Okay. No.
I know you for years.
Okay. Oh, there you go. And it doesn't look well. Okay.
Yeah, voltage. No power, no current.
There you go. Okay, so we have 3 volts on it. You don't see that there's, I don't know, for those of you a little bit away, but there's a marker here. It doesn't read actually that there's no current. There's, I guess, very little current going through here. But we can kind of measure now the voltage across those two and see kind of what we get. And so this is 3 volts range, so.
And remember, the voltage will be the difference in potential between 2 nodes. So we're going to connect
measure
one.
Across both of them.
Yeah.
Yeah, caught it. All right. I'm getting better. Almost. There you go. So 3 across both of them.
Makes sense?
And then if I just across in the middle.
It works.
How come it's 1?
Because it was 1 and 2.
Oh, it was 1 and 2?
I think so. What was the value of the resistors? 1 and 2.
No, 1 and 1. Right?
Was 1 and 1?
1 and 2 or 1 and 1? I forget.
It was 2 total.
Yeah, one of.
Yeah.
It was 2 total, and it's 1 and 1.
Okay, so something's wrong.
Oh, I know what. Hold on. You know, there's always in the demo there's something.
I thought it
Doesn't
was
work.
1 and 2.
3 volt.
3 volts.
That's the weirdest thing I've ever seen. 1 volt. What the heck? Well, I guess voltage dividers don't work.
It still says 3.
What?
It still says 3.
Still says 3.
Take the other one. Are they touching?
What the heck? It's also 1.
Try this one.
I'm kind of freaking out right now. It's
Mickey,
like it's
you're
mess.
killing us.
I know. I don't think it works.
Is your board not working?
Yeah, maybe the board. No, but it's 1 on both. It's like,
Right.
but then across it's 3. It's like ridiculous.
Oh, yeah, this is part of the teaching. When you are in the lab, you have to wear a lab coat and safety goggles, and sometimes things don't work.
What the heck? All right, I don't know what's going on here.
Okay, while you play with that, I'll continue with the lecture,
Yeah, continue.
because there's
Hold on.
more.
Oh, hold on. I just wanted to show the other one.
The other one, okay.
But probably it's not going to work too, so I don't know what happened here. But I'll debug it and figure out.
You will debug. Mm-hmm. Let's see.
Let's see if there's mystery here. That's 3. It's
3
supposed
volts.
to be. Oh, now it works.
Oh, that works.
Oh,
So
you
your
know what-
resistors.
Oh, you know what happened?
Yeah. Go ahead.
When you learn about Thevenin and all that kind of stuff, and about measurements and things like this, you will see that it is important that the device that you're measuring doesn't have actually has very, very high resistance, almost infinite.
Oh, that's what we are going to do today.
And it doesn't, and because we're measuring mega ohms, it's a problem. So this one I try to measure actually small one, it all looks fine. One thing I want to show you though is this.
We could change later.
See what happens?
Oh,
This
yeah.
is a thermal camera. and trying to aim at, there you go. See, the temperature on the resistor is rising. Right, it's like 30 point something degrees, 32, something like that.
As opposed to the other ones.
And then if I connect the other ones, the other ones are not really showing anything hot. And because there's no really current, strong current, because the resistance is so high, there's very little current going through them. Okay? So that's really, so the first one that I did are still pretty hot, so they're starting to cool down, but you know, really it's not changing. But when I put again on the original ones, and I'll even crank the voltage a little bit for you. And you see that they are actually getting quite hot.
Very good. What is that? What's happening there? It's overheating because it's dissipating. We are going to learn that today, too. Okay, perfect. Perfect demonstration. Let's encourage Mickey. We have much more in this class. Okay, so the fact that you can use this, this ratio of resistors to know exactly what's going to be that potential between the two resistors, you can call that this is an operator. And let's put this nice, simple circuit that we now understand on our pockets. And this is going to be one of the tools that we are going to have for design. And today, we are going to do first design. Okay, so first, let's think about energy and power in circuits, which is what we wanted to do here. So in the first, in our first circuits class, we talked about current and what current was, right? So we say, okay, current is flow of charge, flow of electrons that are moving from point A to B. And we had current of electrons here in the classroom going from this side to that side, right? So you could say, another way of writing what current is, you could say that current, let me pick a different color here, that current will be the gradient or of charge with time, right? Because it's current, it's charge moving from one place to the other. Now, we also know by now that it takes energy, it takes some sort of driving force to move electrons, to move charge from one point to the other. What did we call that? We call that voltage. So we will say, okay, so voltage, the voltage needed to move charge from point A to B could be what? The gradient of energy that you see with respect to the charge that you're moving, right? And what's power? Power is the rate of changing energy. So here we saw that there was some energy changing here. There was power being consumed by our resistors, right? So what's this? How do we write this rate of change of energy? So we'll say that the power is going to be the voltage, the energy that we are applying, times the current, which is the change in charge over time. Okay? So with this, we show that power is the voltage that you apply to the circuits, the energy that you are giving for those charges to move, times the current. Now, units. we know that voltage is in volts, current in amperes. So what's the unit for power? Who remembers? Who knows? What? Yes, watts. Very good. Great. So far so good, easy stuff. Now, let's bring this concept of power and energy in circuits, because of course it's an important thing for us to learn, because when we design circuits, we want to optimize them for power consumption, right? We want our iPad and our computer and our phone to last for as long as possible.
I was wondering, is there a difference between big Q and little q?
No, sorry, it's just me writing. Let me fix that. What do you prefer? I think
Q.
little, yeah. The thing is that I write cursive all the time.
It's unreadable.
For Mickey, it's unreadable.
Not just
So
for me.
it's hard for me to write this way. But thank you. Thank you for asking, because I'm sure other people would. I'll be very careful. Okay, so in our analysis and our methods that we are using here, we take an element and we are always looking between the voltage-current relationship. And as you can see here, power also has a voltage-current relationship. So let's do the analysis for an element, any element, and then I'll give you some examples of elements for power analysis. So if I have an element like I have here, a box to start with, I will define the current. We learned passive sign convention last class, so positive, negative, that means I'll draw my current here or I'll draw my current here, right? That's the current, the element current. Now, I will write what we just did for power, and we'll say, okay, the power of an element, or dissipated or produced by an element, is going to be the voltage of the element times the current of the element. So, did you bring your drink? Let's say...
I'll just clap every time.
You will clap? I'm sorry.
Let's do a clapping game, or because I forgot the drinking game.
Okay. So if our element is a resistor, how is the power going to look like? Let's do it. Okay. So I know that power is equal voltage times current. I know that for resistors, I can represent voltage as Ohm's law, right? So I can rewrite this as, okay, the power is going to be equal resistance times current, which is equal resistance I square. Could also be little I here. Okay, so let me just highlight here. This is just from Ohm's law, right? This term. So what's the implication here? In a resistor, we know that a resistor is using power. And when we substitute here the equations by definitions, element definitions, we see that the power here will always be positive, right? Because resistance is a number, has a positive number, and we are multiplying by the square of the current, which will also be positive. So the power in a resistor will always be larger or equal to 0, which means that it will be positive, it will be a positive number. And the convention is that if you have the power being positive, it means it's dissipated power. Okay? So resistor dissipates power. Okay. We knew that already, and we saw here. Getting hot, right? And energy is always preserved. So if you give energy to a system, and the system is using that energy, it will release that energy in other form. In that case, was from heat, which is the answer that you gave here. Okay, let's do this in a different way, because we have a few tools, so we might as well use them. We could also have said, oh, I'm going to go for this power, showing that power is positive in a different way, by element definition. So if I have V element, resistor is R times I element for the resistor, then I can say, okay, that means that the current in the resistor is going to be V element over R, and I want to know what's the power that is being used by this resistor, so power voltage times I. But now I'm going to substitute the voltage as opposed to substituting the current, and then we are going to get V element, I will substitute the current instead of the voltage. V element will be equal to V element over I, and then what do we get? We get V element squared over I, which is also going to be a positive number. Okay, this is for the resistor.
Where did you get the I in the denominator? I was thinking it should be like VL over R. If you
R,
substitute
sorry.
From the previous equation.
No, you're totally right.
No, she just forgot to add the half circle and a leg, but she was going to.
Sorry, and that's why it's positive. If it was I, it would actually be negative. Could be negative, because the current could be the opposite. Let me highlight in a different color. Thank you. I still have my cold brain. Okay, here. Okay? Thank you so much. Yes?
Okay. So if you have like a voltage source, would the power be negative in that case? If you had a voltage source, would the power be negative?
We are going to do all the situations here. Okay. All right. Of course, this is just convention, right? Okay. Now, let's do other elements. I'll pick other elements. What if, let me make space here. What if I pick an open circuit? So I have here open circuit, open circuit. I will draw the current, I element. And then we know that there will be a V element going across here. Okay, what would be the power for an open circuit? Power is equal voltage times I. Okay, so what's the power for an open circuit? 0. How do you know? Because element definition. What's the element definition for an open circuit? Current equals 0. Ah, very good, students. Okay, so we know that because of the definition, this current would be 0. So what's the power dissipated in an open circuit? 0. Seems trivial, seems obvious. We are going to use it today for our design. Let's see, let's pick another element, another useful element, a wire. So if I take a wire, I'll have the voltage across it, I element going this way, and what I want to know is what's the power that's going to be dissipated, used by a wire, because I know that the wire doesn't provide power. Okay, so what's the power dissipated in a wire? Ideal wire. Ideal wire has no resistance, right? If we have some resistance, then it becomes a resistor. Ideal wire. 0. I heard 0 again. Why? voltage, element definition, voltage equals 0, so the power dissipated will be 0. Okay, let's do an example in a circuit that we know, and I have been using this, okay? All we are doing now is playing around with power, so we get that gut feeling for power, and then we're going to do design for power. And I'm going to be asking you questions. Okay, for those who were not here in class, I will repeat a few things that we did last class. So in order to do the analysis for this circuit, which we did, what's the first thing we're going to do? We are going to look about how many nodes we have. This is a simple one. How many nodes do we have? 2 nodes. And then, what's the next step? Choose my reference point as 0. What's the other step? Label the other nodes' potentials that are unknown. Third step, label your currents. Well, there are 2 elements here, so I will label this one as IS for source, and I'll label this current as IL. I call this resistor RL for load, because in a circuit, sometimes when you have something that is using your power, you call it load, especially in power circuits. Right, Nathan? It's the load of your circuit. Okay. Now, what's the next step? Oh, use passive sign convention to label your voltages. So we know that there's going to be a voltage drop around this element, which is our Vs. So I'm going to be consistent and say, okay, here, V element 1, and then here, there will be a voltage across the load, which I'm going to call V load. Good. This is what we did last class. And then we went around to do some definitions. I'm sorry. You make my cough be better. Thank you.
It's a coughing game. Like a cough, you clap.
Okay. But I'm much better than Tuesday. They will tell you, Mickey, it was a disaster, right? 3 words, cough, cough, cough. 3 words. Okay. Well, how are we going to analyze this circuit? We apply our rules now. What's the first rule that we are going to apply? KCL. Oh, does it matter the order? Not really. I'll apply KCL. Okay, so what does KCL say? You pick a node. Are we going to pick node 0? No. It's not an unknown anymore, right? We said this node, I know the potential there. I'm going to say the potential is 0. I'm going to measure everything with respect to that node. Very good. So I'm going to pick node 1 and apply KCL to node 1. So what KCL says? Current that comes into that node has to be equal to the current coming out. How much current is coming in? 0. And what's coming out? That's right. IS plus IL equals 0. Okay, we got one equation. What's the next step? KVL. Very good. So what do we do for KVL? We pick a starting point, we go around the loop, and then we write the voltages. And we know that the sum of the voltages around that loop is going to be equal 0. Okay, so let's apply KVL. So if we apply KVL going around the loop, I'll say voltage. Voltage is potential difference. So let me go potential difference here. U1 minus 0 is equal what? Which voltage? Could be VL, right? If I go here, I'm just doing the voltage definition. Okay, or I could say that U1 minus 0 is also V element 1, right? So I'm going to write that. U1 minus 0 is equal V element 1. How did I get that? I looked at the other side of the circuit, And basically what I'm saying is that if I have a reference here and I'm looking at the voltage drop between 2 points in 2 elements, is the difference between potential, which is U1 minus 0. In one case, we know exactly what that is because it's Vs. In the other case, is VL is the voltage drop in the load, on the load. Okay, so I'm going to write just that, which is equal to Vs.
Question?
Yes?
So when you do case VL, don't you go in a loop and sum up all the voltages and set them equal to 0?
Yeah.
So how come in our equation we only have VL? Wouldn't there be an equation with both VL and VS in it?
Absolutely. What am I doing? I'm just doing each part to write the equations in terms of voltages. And now you can go around the loop and you know what the voltages are because we didn't have the voltages, right? So what I did was I looked at this side of the loop and I said the difference in potential here will be the voltage in this side of the loop, which is this. Then I looked on this side of the loop and I said, okay, the difference in potential here will be this. Now, if we apply KVL, what can we write? We can write, if I go from here all the way to there, the sum should be the same. And we go from minus
We can
up.
see what you're doing.
Really?
Yep.
Oh, okay. So if I go from here, let's go around the loop now. So I can go from here, this is V element 1, and then here, when I go plus to minus, I say minus. So I'll write down for you. It will be V element 1 minus V load equals 0. Which means that was the next step that I was going to do, is equal to VL. Does this make sense? Could we have guessed this just by looking at the circuit? Maybe, maybe not. What does it mean? If voltage definition is that voltage is the difference in potential, and I only have 2 potentials, I have 2 elements, and I'm looking at the difference in potential, I find that the voltage is the same. Thank you for asking that question. Okay, so the definition of KVL is what I did here. I just separate the sides. All right, any other question before I proceed? Okay, this we did last class, much slower, but we did this last class. What we want to do now is power. So let's look at the power here. Power. Power for this circuit. Let's do for element L, which is the load. Yeah? Just apply the equation. The power in the load is going to be the current in the load times the voltage across the load. This is the definition of power that we just went through. Okay, so that means the power in the load is going to be equal to, what is IL? How do we know what IL is? Anybody want to tell me what IL is? Very good. How do we know that's negative IS? Because we did KCL at the beginning, and we can say here IL is equal to negative IS. Excellent. Very good. So I'm going to say here minus IS times VL. Could we do more substitutions here? We could. Let's say that I'm going to write that the power in the load is going to be minus IS times VS. Is that true? Yeah, because we found here that they are the same, right? So I'm just, this comes from KVL. Oh, nice to color things. This comes from KCL. When we are revising, the slides should be easier. Okay? Okay. Let's, we can stop here. Let's do for the other element. The other element is our power source. So that was for the load. I will do the power source here near the power source. So for element 1, which happens to be a power source. Apply the definition of power. Power in the source is going to be current going through the source times V element 1. That's the definition. I'm not inventing anything, just applying the definition. Now we can substitute the values that we know. So we have here that power in the source is equal current in the source times V across the source, which is called Vs. Look at this. So what did we find? We found that the power from the power source is current times voltage of the source. And then we found that the power in the resistor, our element, is current minus current times voltage of the source. What we found was that the power on the load is equal to minus the power given by the source. Or, in other words, the power from the load plus the power of the source is equal 0. This is a very important law in life. What is this?
Whoa. It's conservation of grades.
Conservation of silence. What is this? You have seen this in so many places. It's conservation of energy. When you are solving your circuits or your problems, or you have a problem in life, think about conservation of energy, right? If conservation of energy doesn't hold, something is wrong. Okay? So we just shown here that, okay, there is conservation of energy. That's very important for our next step. Go ahead. And yeah. It's because of the current, the way I put the current. You see here, when I define, I did the same thing as last class where I defined the current. It means that one of these currents is in the wrong direction. Yeah, but okay, but here is not giving you the direction, it's just saying that it's the opposite value of the other one. Subtracting. Okay, let's do a design, shall we? Since this class is called design for something. So today, when Mickey had our first demo, which we'll have more, he took a box, okay? And this box had 2 leads, 2 alligator clips in his case. Mine has 2 leads. And then he said, I'm going to measure the resistance. I'm going to measure the current. I'm going to measure the voltage. And in one case, it didn't work. It's perfect. I mean, it was the perfect demonstration. No, it's not. It was perfect demonstration. So now, the design we are going to have is, let's say, I tell you, please design this, which is a box that can be used to measure voltage. Okay, you would say, are you crazy? I don't know how to design this. I don't think I know how to design this. But we know what the output should be, and that's what we are going to do today. Okay? So how are we going to set up for this design? The problem that I'm giving you is, okay, I have a circuit here, which could be our voltage divider that's right there. And I want you to measure the voltage across the elements of that. How would you measure it? So I'm setting up the design here in boxes. That's what we typically do, box here, box here. This block is going to be doing something. This block has to do something. And then we want to look at the outcome or the output of that block. So with this block, which is called voltmeter, we want to measure the voltage that's coming out of that circuit. Doesn't matter what it is for today, okay? So I'm going to represent this problem, and I'm going to do here with you, so pay attention, and then you are going to get to a point where you're going to do this by yourself. So I'm going to represent this block, this mystery circuit that we want to measure with elements that you know, right? And what are the tools that we have in our pockets at the moment? We know what a resistor does, what a wire does, what an open circuit, voltage source, right? So we will play with the tools that we have. So what I drew here was, inside this box, which in your notes is just said circuit, I said I'll have a voltage source and a resistor. We don't get scared by this, right? We already know how to analyze this. We have done at least twice in this class. But now I'm going to call what we have been called VS as V mystery, because we don't know. That's the point. We want to measure that voltage. And then this R is a resistor that's part of that circuit, because you know that circuit. I don't want to scare you. Then we do the labeling for our circuit analysis. So I have V mystery going here. I also labeled the voltage across the resistor as V element 1. And what we want to measure is the voltage outside here through some leads that we will connect our measurement to, which I'm calling V measurement. Okay, this scribble scrabble here is for measurement, short for measurement. Okay, and the current that I'm defining here outside that I'm going to measure with the leads is called I measurement. Again, scribble scrabble is measurement. Thank you. He forgot. Okay.
Didn't pay attention. I didn't pay attention.
You're paying attention to what I'm doing? Okay. Okay. So let's do it. Yeah? So what's our goal? First, let's define the goal of this project. The goal is to measure, to find out what V measurement is. Because V measurement will be equal to V mystery. Do you agree? What I want is a setup that I can measure voltage here, and my measurement will give me this V mystery that I don't know. Okay, we could apply some rules that we have. First, V element 1. Element 1 is a resistor, correct? So if we use element definition, we can write that V element 1, which is a resistor, is I, current, times resistance. But which current should I put here for our resistor? Which current will be flowing through the circuit? I, measurement. So I know that V element 1 is going to be I measurement times the resistor. Okay, shall we apply KVL? Next rule that next tool that we have in our pockets. So if I apply KVL to this loop here, what would we get? Well, let's see. In this loop I have V mystery, I have V element 1, and then I have V measurement. So this is my loop here, okay? So I'll write KVL. This time I'll write KVL completely. So I'll say V mystery. Is V mystery positive or negative in the direction that I'm going? Positive. Now, next voltage that I have, V element 1. Positive, negative? Negative. Oh, how do I know? Because I'm going from top down. Okay, next, V measurement. V measurement, positive or negative? Negative. Very good. And KVL says that the sum of these voltages will be equal 0. Okay. So let's see what this takes us. This says that V mystery, which is what we want. Oh, you see, cursive will go so much faster. Is equal V element 1 plus V measurement. Well, there is a problem here. Because what I wanted was to have a measurement that gives me V mystery. So what's the only way that I can get to the point where V measurement is equal to V mystery? So that V element is equal 0. Okay. So if I have V element 1 equals 0, but I know V element 1 is a resistor, so I'm going to write one further step saying V element 1 is I measurement times the resistance plus V measurement. And our friend here, front row, said if V element 1 is equal 0, then I have V measurement equals V mystery. Okay, what's the only situation that you can think of, or that we could think of, where this term here, V element 1, is equal 0? If the current is equal 0, because we know that the resistor is a value that we put there, right? So if the current is equal 0, then, oh, that's worse. Then we know that this V element could be 0. Okay, so that means that our measurement has to be functioning as what? Think about your toolbox. What is it that you know? What kind of design could give you an equivalent result that would give you an I measurement equals 0? An open circuit, yes. So, oh, there you go, designers, third class of circuit. So that means that this box here must behave as an open circuit.
I wish I knew that.
You wish you knew that? You see, it was a perfect demonstration.
I don't think it was an open circuit.
I don't think
That
it was
box.
an open circuit. No,
I don't think that box was an open circuit.
it was consuming things.
Yeah.
You had power dissipated somewhere else. Exactly. Why Mickey's first demonstration didn't work? Because his measurement was interfering with what he wanted to do. He was dissipating power somewhere else. And a good measurement only happens when there is no dissipation of energy. Okay? So, energy should not be consumed by the measurement. By the measurement. Let me do this for those that are watching later. Okay, make sense? Okay, here's our first design. So we say that V mystery is going to be equal to V measurement if I measurement equals 0. Cool. Yeah, go for it. Meanwhile, I drink water.
Is there a reason why the voltmeter is not put in parallel with the circuit as opposed to in series?
Yeah. We haven't talked about parallel series, but what could be a reason that you could give me?
We didn't hear you.
Sorry. I said, we didn't teach them yet parallel and series, but tell me what would be a reason for not connecting it in series?
That way you allow current to still run through the circuit while you're measuring it?
Exactly. Would that operate as an open circuit?
I believe it would, because intuitively when you think about like KVL, right, going through the resistor, you know that that potential is going to be, in this case, like V mystery.
Yeah, and that was exactly what Mickey did. But then you have power dissipation. And that's why when you take this box, you have to select different measurements, because there are different circuit blocks that will give you the right equivalent output. Okay. There is a question here. You speak loudly.
And you don't have a loop.
Oh, I made a loop.
Can you repeat the question? Can you repeat the question?
Let me repeat. He said, why does KVL work in this case? Because it looks like the circuit is open. Well, the circuit was not open because it was connected to this, right? I just chose this loop here. And the reason I left it open like this, because we are trying to figure out what's going to be in this box. So when we connect to here, to a measurement thing, we are closing a loop. But I'm not telling you what's inside here. And I'm not saying that there's open wires there. What I'm saying is that the output is behaving as if there was open wires. And that's called equivalence. It's an equivalent behavior.
Yeah, why is V mystery positive? Because if you use passive sign convention, shouldn't it be negative?
It was the way I was doing here. And if I was very consistent, I would have put here V mystery, and then I would put positive. I would put negative to positive, sorry. Negative, positive, and then it would be consistent. Always like from low to plus, I'm gaining, right? Then when we go from plus to minus.
No, but then isn't I measurement coming out? So shouldn't it be positive to negative?
Say it again.
Like, wouldn't I measurement be coming out from the positive side, like how you drew it?
The voltage is KVL. I'm just looking at a loop in the voltage. So I'm not looking at the current. I'm looking here, I'm saying I'll start here, I'll go here, positive, negative, negative. That's what I did. I didn't consider the current for KVL. I considered the current in the, if I would do KCL.
Wait, but isn't
which I didn't use here.
Isn't your sign convention dependent on your current?
I can't hear him, Nikki.
Isn't your sign convention dependent on your current? Like which direction you took the current?
Yeah, and I measurement is for this element here, which is this mysterious element. So it's going into the positive, and I could draw this way the current. I measurement and V measurement is for this box, which I took it out here because this box is part of this loop. Yeah? All right, let's do the other side, how to measure current. Ready? So now you know how I'm thinking here. Think with me. So the problem now is, how do you measure current? Okay, how do you measure current? Same problem. I have a circuit. I have a box that I want you to come up with a model for how you would measure current. So our goal now is to measure I mystery. Okay, what did I do here in this setup? In this setup, I included a current source, which I'm saying is I mystery, is what I want to find out. What's the current in this circuit? Now, I added a resistor here. You did this in discussion, this circuit. Current source and a resistor. This is the circuit that I want to figure out what's the current going on there. Then, I labeled here IR for the current going through the resistor. And then the current in the measurement, I measurement. And the voltage across here, the voltage for this element, measurement box, is V measurement. So which law, which tool would you apply for this circuit to see how this circuit is operating? When we were measuring voltage, we applied KVL. What are we going to apply here if what we want to measure is I mystery? KCL, exactly, KCL. And what KCL says? You pick a node, and you know that the currents coming into that node has to be equal to the currents coming out of that node. So, let's pick a node. Let's pick this node here. Let me color it. We have different color. So if I take that node, what is the current? The currents coming into the node. I mystery. Very good. I mystery, and this will be KCL. Okay. What are the currents going out of the node? IR, which is the current going through the resistor, plus I measurement. Very good. Okay. So since I wanted to get I measurement to figure out what is I mystery, that means that I have to be in a setup, I have to have a setup where I mystery is equal to I measurement. But I have this current, this IR here in the middle. That means I want this to be 0, right? But that is the current going through a resistor. So let's write the element definition here. And I will say I mystery is equal, if I apply Ohm's law to it, what's IR? What's the voltage that I can use, voltage element for IR? It's going to be V measurement over R plus I measurement. So, in order for you to have that term here, this current IR to be equal 0, what needs to happen here? Resistor is not 0. That means V measurement has to be 0. Okay, so I mystery is going to be equal I measurement if V measurement equals 0. Okay, so that means that in your design, your box that is measuring current has to behave as which element? A wire.
A wire.
A wire. So this box has to have the equivalent output of a, if it was a wire. Okay. Has to behave as a wire. Okay. How are we doing in time? Oh, good.
So I got lost about how IR went to 0, did we assume that it's going to be 0 or?
It's an assumption, right? Because what I want in this design is I have eye mystery that I want to measure. And I want that eye mystery to be equal to my eye measurement. But when I apply KCL, I see that there is another current term there. And that current term has to be 0, otherwise I can't do that measurement.
Oh, got it.
Yeah? Very good. Okay. So this is your first design. Now what you're going to do in the lab, your next lab experiments, is touch screens. So you're going to design models for how touch screens work here, and you are going to actually build touch screens in the lab, which is pretty cool. So what's a touch screen? A touch screen, we all use touch screen all the time, right? Either in a phone or the iPad. And one of the first models of touch screens were actually that you had to press and things would move in order for you to get a signal from the screen. There's still some places where you do that, where you have, it's actually a mechanical energy that then is used to have the signal. So that's what you're going to do in the lab. Your parts, the parts for the lab look like this. I have some parts here too. And you'll have one board that's going to be the bottom plate of your touch screen with where you will have some resistors. I believe the resistors are already there for you. Some wires. And then you're going to put some spacers in between such that you have this flexible array of resistors that will be overlaid with the rigid array of resistors with those spacers in the middle so you can press and make contact between metals, okay? So the first thing we have to do is to understand resistors and materials and how the materials behave when you have different resistance. Because in a touch screen, where's my pencil? In a touch screen, you will have this flexible layer. This flexible layer is usually done with a material that's called ITO, which is indium tin oxide. It's transparent and conductive. It's in all of your screens. All of them have ITO. And then you have either, you have your rigid screen there. Okay? So what's important there? So you pick these materials based on their properties. And the property that you're interested very often is the play between transparency and resistance. So here, transmittance is a measurement of how much light that material gets through. Like a window. A window has very high transmittance, while wood has very low transmittance. Light doesn't go through it. Then you measure what's so-called sheet resistance, which is a property of the material, which will tell you how good of a conductor that material is. So in this plot that I have here, it's giving you what are the requirements for such films or transparent resistors for photovoltaics, for lighting, for the screens that you have here in, in your computers, and then other capacitive and resistive touch screens, and then some other treatments for antistatics, and the materials that we use. So, do you think we have time to do the demonstration today?
Sure.
Yeah? So what we did here, we brought a bunch of materials to show you what's the relation between property of the material, which is something that you don't change. It comes for, it's part of the material, which is called conductivity. But there is one thing that you do change using these materials is how to make the wire, and that's related to the geometry of the wire and how you choose to set it up. So what we have here is one material. Which material do we have?
Switch.
Oh,
So do you know which material is this? Oh, where's the pens? The small ones.
the small ones are here.
So this is graphite. Graphite is it's a form of carbon. You use that in pencils, and it turns out it actually is conductive, albeit not a great conductor. And so it is going to have a sheet resistance much higher than that of
Keep going. I'm
than
looking.
that of copper. And we can actually go and measure it. I'm gonna right now just put measurements on. Oh, do we have a small one?
Yeah.
Actually, that one's better.
You want a small one? Be careful. So you write with conductors all the time.
Yeah, you're right in conductors. It's pretty cool. Here's one side. Here's the other side. And this one is 3.7 ohms. Okay? 3.7 ohms, actually 4. It changes a little bit because the way that you touch the conductor also has what's called a touch resistance.
Contact resistance.
Contact resistance. And so it doesn't look like it's changing, but that's because the contact resistance in this case is much higher than the resistance of the material itself. So this one is about, I guess, 5 ohms. This particular, so it's, I mean, if you took a wire that's made of copper that length, then it would be, you wouldn't be able to measure it. It's so conductive. Okay, so here we were able to measure it. I think what we're going to do now is we'll just put that through.
Yeah.
So this is a rod. We're going to connect the rod. Okay, you're going to hold this
Absolutely.
with 2 hands.
Yep.
So you can see.
Yep.
And I'm going to start applying voltage to it. Oh, well, that's a lot of amps.
Oh, it's singing.
Okay. So right now I'm just going to increase the voltage.
It's getting hot already.
No, so I turn it off.
Okay.
So I am putting about half a volt in, and it's measuring 1.4 amps. You multiply it together, you get about 0.7 watts. But then I can just keep going. And now it's getting to the maximum of what this power supply can actually do, which is 5 amps. 5 amps times 1 volt, that's 5 watts. Okay. So it's probably getting quite warm now. And when I, ooh, wow.
Oh.
Ooh, cool.
Yeah.
So yeah, it's getting warmer and warmer and warmer. Can you see the value? Can you lower it?
33, 34, 35 degrees Celsius.